Hi class, so ready to start into chapter 6. So chapter 6 is over analytic trigonometry. Section 6.1 is titled Fundamental Trigonometric Identities. So if you enjoy like algebra type things, then you should like this type of section, because this section is gonna focus a lot on like algebraic skills, right? So I have here just a table, right? So these are the fundamental trig identities that we've seen from chapter 5, right? In a nice table format. So we have the reciprocal identities, quotient identities, Pythagorean identities, and also these even odd identities, right? So you want to make sure that you know these identities. And essentially what we're going to be doing is using these and substituting them in to other equations and trying to simplify things, right? So not a lot of like new material, right? It's just more like algebraic type things, and maybe something you've never done before, done a lot with, is verifying identities. So I'll show you how to do that, right? So example 1, we're asked to simplify the following. So we want to write the final, and also we want to be able to write the final form with no fractions. So we have tangent of x times cosine squared x times secant of x, right? And so if thinking about this one a lot, something that can help simplify it is we can put everything in terms of cosine, right? Because cosine squared x is obviously in terms of cosine. Secant can be 1 divided by cosine, and tangent we can have be sine over cosine, right? And sometimes these don't come super obvious to you, so you just got to kind of play around and figure out what works, right? So we want to be able to answer the directions, right? So what we have is tangent of x times cosine squared x times secant of x, right? So what I'm going to do is use the quotient identity for tangent, which is sine x over cosine x. And then cosine squared x we could rewrite as cosine x times cosine of x, right? And then lastly, secant of x is 1 over cosine x, right? That's reciprocal identity. So then what you're going to see here, is if it helps, I can put these over 1, right? So these cosine x will cancel out. These cosine x will cancel out. So notice what you're left with is just sine of x, times 1 all over 1, which is simply just sine x, right? So we've met the conditions, right? We've simplified this, and our final form has no fractions, right? So this is what we are after, right? Just sine x. Right. So example 2, we have the same directions, but we have a little more difficult expression. We have cosine theta over sine theta plus sine theta over 1 plus cosine theta. So let me just start by writing that down. So we got cosine theta over sine theta plus sine theta over 1 plus cosine theta, right? So maybe the first thing to do is to get common fractions, right? So we need to, get common denominators, right? So then we can add the fractions together, right? So this would be equal to cosine theta over sine theta. So I can multiply by top and bottom by 1 plus cosine theta, right? So I'm thinking the common fraction is just common denominator for the fraction is just multiplying the two denominators together, right? So then we'd have plus, and then we'd have sine theta over 1 plus cosine theta. So what we need to multiply the second fraction by is sine theta over sine theta, right? So notice we'll get the common denominator then, right? So this would be equal to cosine theta times 1 plus cosine theta all over sine times 1 plus cosine theta, and then plus we would have sine squared theta all over sine times 1 plus cosine theta. Right? So now notice we have common denominators, right? This denominator matches this denominator. So we can add these fractions together to get cosine theta times 1 plus cosine theta plus sine squared theta all over sine times 1 plus cosine theta. Right? And then kind of the next thing I'm paying attention to is I have sine squared theta here. And if you notice, if I take cosine theta and distribute this through, cosine theta times cosine theta, that's going to give me cosine theta squared, right? And we know one of the Pythagorean identities is, cosine squared plus sine squared equals 1. So that's going to be able to simplify that a lot more, right? So I'm just going to distribute the cosine theta through in the top. So we would have, cosine theta times 1 plus, and then cosine theta times cosine theta is cosine theta squared. This would be plus sine squared theta all over, I'm just going to leave the denominator how it is, sine, wait, no, that should be sine theta. Right, let me make sure I write that correctly. Sine theta. Right, because it's sine theta times 1 plus cosine theta, so that does make a difference, right? So this would be sine theta times 1 plus cosine theta. Right, so then again, what I'm thinking about is this guy is just equal to 1, right, using that Pythagorean identity. So what we get is cosine theta plus 1 all divided by sine theta times 1 plus cosine theta, right? And then so now you'll notice that I have a common factor in the top and bottom, right? It might help if I put parentheses just around the numerator, because you can see that both of these guys are the same, right? So if I divide top and bottom by 1 plus cosine theta, what's going to be on the top is 1, so you're going to have 1 over sine theta, right? So we're getting a lot closer, right? My answer is a lot more simplified, but I want no fractions, right? So I can easily not have a fraction here, because 1 divided by sine theta is equal to cosecant of theta, right? And that's one of the identities. So that whole expression is just equal to cosecant theta, right? So notice so far we're just working some things through algebraically, right? So not too terribly difficult, right? Not a lot of new material, right? Just focusing on the algebraic skills, right? With trig. So example 3, we want to simplify. So same directions as before. We want no fractions in our final answer. So we have 1 minus secant squared t all divided by tangent t minus tangent t secant t, right? So the first thing that we could notice is that I could factor the numerator, right? Actually, factor the numerator and denominator in this case, right? That will help me simplify this, because notice this is the same thing as 1 squared minus secant squared t all over, and then I can factor out a tangent t in the denominator, so this would be 1 minus secant t, right? And this top part, right, that you should recognize this. This is called a difference of squares, right? So you may have seen, something like this before, where if you have a squared minus b squared, this is equal to a plus b times a minus b, where we have difference of squares, right? So maybe a quick example of this would be like x squared minus 9, right? X squared minus 9 factors would be x plus 3 times x minus 3, right? Something that you should have mastered in algebra, right? And seen again in college algebra. So so noticing that the top is a difference of squares, we can factor that. So this would just be equal to 1 minus secant of t times 1 plus secant of t. And then in the denominator, we could just keep it the same. So tan t times 1 minus secant t, right? And then you'll notice, since everything's multiplied top and bottom, I can divide top and bottom by 1 minus secant t. So that will cancel out, right? Those things will cancel out with each other. So what we end up getting is 1 plus secant t all over tangent t, right? So then the next thing that I want to do is this expression is simply the addition of two fractions. So I want to split it up, right? So, similarly, if I had like x over 4 plus 1/4, this equals, x plus 1 over 4, right? So kind of the idea is we're starting here, and I can split it up into these two fractions, right? So I want to do that same thing here. Right, so this would be equivalent to 1 over tan t plus secant t over tan t. Right? So in other words, I'm thinking about like two separate fractions like this, right? Where you take each term in the top over the denominator. So 1 divided by tangent of t is equal to cotangent of t, right? And then, in terms of secant and tangent, well, secant we know is 1 over cotangent of t. And tangent is sine of t over cosine of t. Right, so I'm substituting those, quotient and reciprocal identities n to see if we can try to simplify this a little more. Right, so what I can do is just keep going here. So we would have equals cotangent of t, and then plus, and then I'm gonna rewrite this with how we divide fractions, right? We would have 1 over cotangent of t times the reciprocal. Whoops, and I wrote cotangent here, but that should I think that's cosine. Right, so just fix that in your notes, right? This part here should be cosine. So this would be 1 over cosine times sine t. Oops, let me grab black again. Sine t. Oops, we need a times the reciprocal. So it'd be 1 over cosine t times cosine t divided by sine t. Right, so what will happen is these two things will cancel out. So this is equal to, we'll have cotangent of t plus 1 over sine of t. Right? So then this would be equal to cotangent of t plus, and then 1 over sine t is cosecant of t, right? Because remember, the whole idea is we're trying to simplify and not have any fractions, right? So that's as far as we can go, right? So that's the simplified version of our original expression with no fractions. All right. So now that we practiced that skill, the whole idea with being able to do that skill, so then we can do objective 2, which is the verified trig identities, right? So essentially what's going to happen is it's going to be like example 1, right? So I have here, in example 1, we showed that tangent of x cosine squared of x times secant x is equal to sine x, right? So this is an identity, right? So we're going to verify that, right? So so how we're going to verify that is we're going to start with one side and try to simplify it, algebraically, to make it equal to the other side, right? So in other words, what we want is we want to like start with the left-hand side essentially and make it equal to the right-hand side. We want to show this, right? So this is kind of like a real simple type of proof in mathematics. When you start to learn proofs, this is something that you kind of start with, and it's essentially what we're doing is doing almost like a direct proof, and we're not doing it super formal. So if you keep going in mathematics, you might you'll learn how to write up proofs a little more formally, but we're kind of flirting with that here, right? So example 4, we want to verify that this equation is an identity. So we have sine of negative x times cotangent of negative x divided by cosine of x is equal to 1, right? So let's just start, with the left-hand side. So the left-hand side of the equation is equal to sine of negative x cotangent of negative x all divided by cosine of x, right? So we're just going to keep simplifying it and try to hopefully get down to 1, right? So first thing I notice, since we have the negative x inside, both sine and cotangent are odd functions, right? So what this is going to equal is negative sine of x times negative cotangent of x all over cosine of x. Right, so all I did was substitute these two spots for their even-odd identity, right? And they're both odd functions. So then these two negative signs here, right, they are going to cancel each other out, right? It's essentially like negative 1 times negative 1 times sine x times cotangent x, right? I can rewrite it like this. So this part is just equal to 1, so they get rid of each other, if you will, right? So then what we have is sine x times cotangent x all divided by cosine x, right? So then remember, we're trying to get the 1 from this. So notice I have a sine here, a cosine, and cotangent. Well, something nice and convenient is I can rewrite cotangent terms sine and cosine. So let's see if that gets us there, right? So this would be equal to sine x, and cotangent, is equal to cosine x over sine x. So I can just fill that in. This would be all over cosine x, right? And I'll put sine x over 1 if that makes it a little easier, right? And there's a times here. These are being multiplied. So notice what's going to happen is these sine x's are going to cancel, and what we're left with in the top is just cosine x, and then in the denominator is cosine x, right? So cosine x divided by cosine x, well, that's just going to equal 1, right? So in other words, this is going to equal the right-hand side, right? So we've shown that the left-hand side equals the right-hand side, right? So in other words, it checks out. We verified the identity, right? So when you verify an identity, that's what we're doing, right? We start with one side and show it's equal to the other side. All right. So ready for example 5. So we want to verify that this equation is identity, right? So similar idea, right? We have the left-hand side, which is equal to 1 over 1 minus sine x minus 1 over 1 plus sine x. So, again, we have like two fractions being subtracted with different denominators. So maybe what I would start by doing is trying to get common denominators with the fractions, right? So, again, an easy way to get common denominators is just to multiply the two denominators together, right? So what we would have is 1 over 1 minus sine x times 1 plus sine x over 1 plus sine x, right? So multiply the first fraction times, denominator of the second. Then we'd have minus, and then we'd have 1 over 1 plus sine x. And then I can multiply this by 1 minus sine x over 1 minus sine x, right? So we're just multiplying each fraction by 1, but getting a different denominator. So this would be equal to 1 plus sine x all over 1 minus sine squared x, right? So you have to, FOIL this, right? So 1 minus sine x times 1 plus sine x, right? That's a difference of squares, right? This would end up being, 1 times 1, and then plus 1 times sine x plus 1 times negative sine x, and then plus sine x times negative sine x, right? Simplify that and you just get 1 minus sine squared x, right? So then the second one we'd have minus, and then we'd have 1 minus sine x all over 1 minus sine squared x. So we got a common denominator now. So this would give me 1 plus sine x minus 1 minus sine x all over 1 minus sine squared x. So we need to distribute this negative through, right? So what this gives me is 1 plus sine x minus 1 plus sine x all over 1 minus sine squared x. So simplifying the top, we get 2 sine x, right? Because the 1 minus 1 is 0, and then we have 2 sine x's, right? Sine x plus sine x is 2 sine x, right? And then another thing to pay attention to is this denominator, right? So we have 1 minus sine squared x. Well, we know a Pythagorean identity is cosine squared x plus sine squared x equals 1. Right, so this kind of looks like this, right? If I subtract sine squared x from both sides, what we end up with is cosine squared x equals 1 minus sine squared x, right? Which matches exactly with that expression. So I can substitute that expression for cosine squared x. Right? You might be wondering why I want to do that, right? But pay attention to what we're trying to get, right? Our whole goal is to get something that looks like this. So if you notice, I already have the 2 part, and notice these parts are tangent and secant. So I want to try to, tangent is sine over cosine, and secant's 1 over cosine. So I'm trying to get like a cosine in the bottom, right? Which we did. So this is equal to 2 times sine over cosine squared x, and this is the same thing as 2 times sine over cosine x times 1 over cosine x, right? So trying to break this apart, right? Like basically like multiplying fractions in reverse. So then what this becomes is 2 times, and then sine x over cosine x is tangent x, and then 1 over cosine x, like I said, is secant x, right? So we're able to get exactly with the right hand side, right? So this equals the right hand side, which is 2 tan x secant x. So we verified the identity. Right. So then example 6, we want to verify the equation's identity. We have 1 minus sine squared t over 1 plus cosine t equals cosine t. So again, just start with the left hand side. So we'd have 1 minus sine squared t all over 1 plus cosine t. So this is equal to, so again, let's try to get common denominator. So this would be the same thing as, 1 plus cosine t over 1 plus cosine t, right? So I'm just rewriting 1 with the same denominator, right? This would be minus sine squared t all over 1 plus cosine t. And so this equals, we'd have 1 plus cosine squared t minus sine squared t all over 1 plus cosine t. Right? So then, what I could do is I could change the order of these two terms. Right? So this would be 1 minus sine squared t plus cosine squared t. Right? That's just using the commutative property of addition. Right? Divided by 1 plus cosine t. So then 1 minus sine squared t, we already saw is equal to cosine squared t, right? Right here. So this would be equal to cosine squared t plus cosine t all over 1 plus cosine t. Right? Now we're getting closer, because now what I can do in the top is factor out cosine t, right? Because that would be cosine t times cosine t plus 1 divided by 1 plus cosine t. Right? Well, these two factors here can cross out, right? And what we're left with is just cosine t, which is what we're after, right? That's equal to the right-hand side. So that's verified. All right, so now we're ready to work on example 7. Oops, hang on. Right, so with example 7, something that I think will work well here is if we actually cross multiply, right? This it's kind of set up like a proportion, right? So what we would get, is 1 minus cosine of x times 1 plus cosine of x equals cosine of x times tan x times sine x. Right? So, these two statements are equivalent to one another, right? So if I can show this one to be true, it's the same as showing that the original is true. So this is just a little easier to work with, right? So 1 minus cosine x times 1 plus cosine x, right? This would be, 1 squared minus cosine x plus cosine x minus cosine squared x, right? Just doing, foiling this. So what we end up with is so essentially I'm trying to work, one side of the equation, right? So 1 squared minus cosine x plus cosine x minus cosine squared x. So what we did is, like I said, just FOIL this left-hand side. So let me write that out a little better. Let me say, left-hand side equals this, right? So then this would be equal to 1 minus cosine squared x. And then, so following, using Pythagorean identity, right, which is sine squared x plus cosine squared x equals 1. So notice here we have 1 minus cosine squared x. So if I subtract cosine squared x from both sides, what we get is sine squared x equals 1 minus cosine squared x. So I can substitute this in. So this is just equal to sine squared x. Right? So then now let's work with the right-hand side. The right-hand side is cosine x times tan x times sine x. So I want to try to make it look like the left-hand side, which is just sine squared x. So this would be equal to cosine x times, so tangent I can rewrite as sine x over cosine x, and then we'd have, times sine x. So the sine, or the cosine x's will cancel each other out, right? So then what we're left with is sine x times sine x, which is sine squared x, right? So what we've shown, right, is that the left-hand side is equal to the right-hand side, right? So we follow the directions, right? We manipulated each side of the equation independently, right, and shown that they're equivalent to each other, right? So that's identified. Right, so then example 8 is we want to verify this equation's an identity. And we have some, tangent, sine, secant, and cosine squared in this. So there's a couple of things that we're going to use. One is that if we start with the Pythagorean identity tan squared x plus 1 equals secant squared x, I can subtract 1 from both sides, and this becomes tangent squared x equals secant squared x minus 1, right? So we're going to use this in this problem. And also, if we start with cosine squared t plus sine squared t equal to 1, if I subtract sine squared t from both sides, we get cosine squared t equals 1 minus sine squared t. And then if I multiply both sides times -1, what we get is negative cosine squared t equals sine squared t minus 1. Right, so we're going to use this in this problem as well. Right, so I'm just working these ahead of time so we can easily use them. And so notice our variable's t the entire time. So if we wanted to, right, I could get rid of these x's in the first one I did. And just replace it with a t, and it's the same thing, right? Right, so we're going to use these in our proof, right? So the left-hand side is equal to tangent squared t plus sine squared t. So then I'm going to substitute the first this first one in here, and for tangent t, so this would be equal to secant squared t minus 1, and then I'm just going to write plus sine squared t, right? And then so notice what we're trying to get to. Remember, the whole goal is to get to this right hand side. So notice that, secant squared t, I can check that off. I already got that. What I want is I want this part to be equivalent to negative cosine squared t. So I'm trying to work that out. So it turns out, that this would be equal to secant squared t. And we can swap the order of these two terms, right, using the commutative property. So this would be plus sine squared t minus 1. And then we know, this part is equivalent to negative cosine squared, right? So this would be equal to secant squared t minus cosine squared t, which is exactly what we wanted, right? So this is equal to the right-hand side. So we verified that, right? Alright, so we got 2 examples left. So the next objective we want to look at is writing an algebraic expression as a trigonometric expression. Right, so I have at the top here that, in some applications of calculus, which this course is, some of you might be stopping at trig, but ultimately trig is to help prepare students for calculus. So it's oftentimes in calculus we might want to write an algebraic expression of the form, so they got 3 forms there, as a trig expression by way of an appropriate substitution, right? Sometimes that might be easier for us to work with. So that's just what we're going to practice here. So example 8, we want to write the square root of x squared plus 25 as a function of theta, where theta is in between 0 and pi over 2, by making the substitution x equals 5 tangent of theta. Right? So, we have the square root of x squared plus 25. So we're just going to plug, this in for x. So this would be equal to the square root of, 5 tangent of theta quantity squared plus 25. Right? So here, right, this would just be equal to the square root of, this would end up being 25 tan theta. Right? So we'd have to take 5 tan theta times 5 tan theta, which gives me 25 tan squared theta. And then we'd have plus 25 still. So what I can do now is I could factor out a 25 from this. So we get tan squared theta plus 1. So then this would be equivalent to, so tan squared theta plus 1 is a Pythagorean identity, right? So this would be equal to the square root of 25 secant squared theta, right? Because tan squared theta plus 1 equals secant squared theta. So then, using properties of radicals, I could split this apart to be radical 25 times radical secant squared theta, which this would be equal to 5 times secant theta. And something we have to think about here is, since I'm plugging in a trigonometric expression in for here and for x, right? We might be losing the sign of this guy, right? So if we think about since theta is in between, basically theta is in the first quadrant, right? Theta is somewhere in here. All the trig functions are positive in the first quadrant. So it turns out that this would end up being positive. So I don't have to worry about putting a sign in front of that, right? So same thing with example 9 in terms of the sign of the trig function. We're in between 0 and pi over 2 again, so all my trig functions are going to be positive, right? So I don't necessarily have to worry about that as much, right? Because if I square something and then take the square root of it, I'm going to lose what the original sign was, right? So like if I take, -3 squared and then take the square root of that, right? Well, this would, be the square root of 9, which is just 3. So we lose what the original sign was of the original thing, the original item, right? So you just got to be careful with that. Right? So this next one, same thing, right? We start out with the expression, which is x squared minus 121. Then we're going to substitute 11 secant theta in for x. And then we're just trying to simplify it, right? So this would be 11 secant theta quantity squared minus 121. So 11 secant theta squared would be the square root of 121 secant squared theta minus 121. And then I could factor out a 121 again, like before. So this gives me secant squared theta minus 1. Secant squared theta minus 1 is tangent squared theta, right, using Pythagorean identity. So this would be the square root of 121 times tangent squared theta, which is equal to, so using properties of radicals, this would be radical 121 times radical tangent squared theta. Right? So this equals 11 tan theta, right? After taking the square roots of both of those, right? And same as before, right? We don't have to worry about the sign is going to be positive because of our restriction on theta. All right, so that's all I have for this section. So make sure you're keeping up with the class and let me know if you have any questions. Thanks.